So as we discussed in the first part of the lecture, we have a data set D, which is a set of points xi and yi, where I goes from 1 to m, and each of the xi's is a real vector or k-dimensional real vector, and each of the yi's is binary. So we want to learn a functional mapping fw of phi of xi that maps, that learns the degree of belief as to yi being 0 and yi being 1. So the function f not just it doesn't just output 0 or 1, it learns the degree of belief or some quantitative value that quantifies, that represents that degree of belief. It quantifies that degree of belief into y being 0 or y being 1, right? So that is the function will output the probability of yi being 0 and probability of yi being 1. So to simply put, we are going to learn a functional mapping on the data set. We learn a stochastic model, as this function is a stochastic model. On the data set D, that learns to generate the probabilities, or more specifically the conditional probabilities of yi given the input xi and some parameterizable variable w. So today we are going to learn this stochastic model that learns to generate these conditional probabilities. That is, instead of just outputting 0 or 1, it outputs the probabilities, the conditional probabilities of yi being 0 or 1. So this problem today we are going to learn an algorithm which solves this problem, and that is logistic regression. So logistic regression is a kind of regression where each of the yi's is binary. Is yi is binary, 0 or 1. And the yi's follow binomial distribution. So it is not important for this lecture to know exactly what is binomial distribution because we will be anyway covering it in the later part of this course. So to summarize it, we are going to learn the functional mapping on some phi of xi, which outputs the conditional probability of yi given the input xi and some parameterizational parameter w. So this y is not conditioned on w, the w is just a parameterization function for this conditional probability distribution. So y's can have different meanings and different interpretation. For example, if you consider problem of classification in particular, for example, if you consider image classification problem, then the goal is to know whether this particular image for example, the problem may consider that this particular image has particular class of obstacle that we want or not. For example, if that obstacle is present, then the label can be 0, and the obstacle is absent, then the label can be 1. And we also know the probability of that obstacle being present or not. For example, that obstacle can be very vaguely present in the image, it's not very clear. So we also want to know the conditional probabilities as that particular image containing that particular obstacle or not, right? So this is one interpretation of like yi and this conditional distribution basically. So yi here like 0 means class 0 and y here 1 means class 1, where 0 is a class of images which have that obstacle and 1 is a class of is a set of images that do not have that obstacle. Likewise, for example, if we are doing a coin toss, then in that case y equal to 0 may represent head and y equal to 1 may represent tail. So perhaps like y equal to 0 heads means success and y equal to 1 means failure. So depending on the data set and depending on the problem that you're solving, yi's can have different interpretation. And these yi's follow a binomial distribution. So we're going to learn this functional mapping. That takes in the non-representation of the input data points and it learns the conditional probability distribution. Right. And any probability distribution has some properties. For example, this P has to be less than 1 and should be greater than or equal to 0. Right. So this function should satisfy this property. So like in linear regression, we consider this functional mapping to be phi of xi transpose times w. That is the function was linear in its argument, right? So this kind of function is not bounded. For example, we can plot the response of the function with respect to its input feature vector. So assume if phi is a scalar, right? This is phi xs and this is f of phi, right? So as you can see, since this is a linear, the range of this function is basically from negative infinity to positive infinity. That is, the function is unbounded both below and above, right? It will pass through origin. It will pass through origin. So you can see as phi goes to infinity, the function will go to infinity. As phi goes to negative infinity, the function will go to negative infinity. Depending on the sign of w, that may change basically, right? So this kind of function doesn't satisfy this property, right? So this is a bad choice for learning the probabilities because this function is unbounded below and above. So today we are going to consider a special function known as logistic function that satisfies this property. Right. So that function is logistic function, and that's why the name of the algorithm is logistic regression. Is a logistic function. So now let's see what is a logistic function. So a logistic function g of its argument t, where t is a scalar or real scalar, is simply 1 over 1 plus e to the power negative of t. So this function, if you plot this function, it satisfies the constraint. The range of this function is between 0 and 1. So if we plot it, sorry, it looks something like this. So this value, so asymptotically, it converges to 1 as t goes to infinity. Right. So the limit of the function as t goes to infinity is 1. And as t approaches negative infinity, g of t is 0. So this function satisfies the constraint. Right? So today we are going to learn this functional mapping on the data set. That is, our function fw of phi of xi is g of phi of xi superscript I transpose times w, which is 1 over 1 plus e to the power negative of phi of xi transpose times w. So as this phi of xi transpose w approaches infinity, the limit of g is 1, and as this approaches negative infinity, the limit of g is 0. Right? So it satisfies that property. So here fw of phi of xi is simply g of phi of xi transpose times w, which is equals to conditional distribution of y given xi and it's parameterized by w. So today we'll teach you the logistic regression, and we'll compute the optimal solution, which is going to be the next part of the lecture.